Hello. Today we're going to start the discussion of optimization. We're going to discuss the same topic in next section. Optimization means to pick the best choice from different options. Let's start from the concept of absolute extrema. We talked about relative extrema before. Those are the maximum or minimum values of the functions locally. The absolute extrema are the maximum or minimum values of f in the whole domain. So if f of x is less than or equal to f of c for all x in the domain of f, then f of c is called the absolute maximum value of f. And similarly, if f of x is greater than or equal to f of c for all x in the domain of f, then f of c is called the absolute minimum value of f. So take a look at the picture. We have a piece of curve on the graph. There are four extrema on the curve, A, B, C, and D. The point A is a relative extrema or relative minimum. It is minimum locally, but it's also the absolute minimum because it's the lowest point on the curve. So it is relative and absolute minimum at the same time. The point B is a relative maximum, but it's not the absolute maximum because it's not the highest point on the curve. Point C is relative extrema, is relative minimum, but not the absolute minimum because it's not the lowest point on the whole curve. Point T is the absolute maximum, but it's not the relative maximum because we don't have the curve on the right side of the point D. So let's just do a simple example to start. We want to find the absolute extrema of the function f equals x squared on the closed interval from -1 to 2. So when you try to find the absolute extrema, you need to do two steps. Step 1 to find the relative extrema. Step 2 to compare the relative extrema with the endpoints, because the endpoints are not considered in the first step, and they can appear as absolute extrema. So let's start from finding the derivative of f. We got f prime equal to 2x, and we set it 0 to find the critical number x equal to 0. And if you take the second derivative, you get the f double prime equal to 2, which is possible. So by the second derivative test, we know f attains a relative minimum at the x equal to 0, and the f of 0 is just a 0 squared, which is 0. Then we compare this relative minimum with the endpoints at the x equal to -1 and the x equal to 2. So at the x equal to -1, plug in -1 for x, we got f of -1 equal to -1 squared, so that's 1. At the x equal to 2, plug in 2 for x, we got f of 2 equal to 2 squared equal to 4. So both are higher than the minimum, obviously, but the absolute maximum will occur at the x equal to 2. So f attains the absolute minimum of 0 at the x equal to 0, and the absolute maximum of 4 at the x equal to 2. Now let's do an application problem for using optimization in economics. The quantity demand of a certain brand of handbags per day, X, is related to the unit price P in dollars by the equation of P equals 100,000 over 250 plus X minus 100. And then we consider X from 0 to 750. Find the level of sales and the corresponding unit price of the handbags that will result in the maximum revenue per day for the company. And what is that revenue? Okay, so we just start from the revenue function R, which is the product of X times P. Remember, X the quantity and P is the unit price. So we get X times 100,000 over 250 plus x minus 100. So we got 100,000 x over 250 plus x minus 100x. Take the derivative, so we get r prime equals 100,000 x prime times 250 plus x minus 100,000 x times 250 plus x prime over 250 plus x squared. So that's just the quotient rule. And minus 100. You can simplify this expression and set that equal to 0 to solve for the critical number, and we get the x equal to 250 if you do some simple algebra. You can further take the second derivative function of revenue, so you got the negative 50 million over 250 plus x cubed, and that's negative. So according to the second derivative text, the revenue Rx, it ends relative maximum at x equal to 250, and the actual revenue at x equal to 250 is 250 times 100,000 over 250 plus 250 minus 100, and that is $25,000. So we can compare this relative maximum with the endpoints at x equal to 0 and x equal to 750. So just plug in 0 for x. We got r of 0 equal to 0 times 100,000 over 250 plus 0 minus 100, and we get 0. Similarly, plug in 750 for x. We get r of 750 equals 750 times 100,000 over 250 plus 750 minus 100, and again we get the 0. So obviously the maximum revenue occurs at x equal to 250, and the actual revenue is $25,000, with the price equals 100,000 over 250 plus 250 minus 100, which is $100 if you plug in the function p. So this is the end of this section.